What do you mean by motion? What is uniform motion? What is non-uniform motion? What are those two parts? The first you would say is uniform circular motion, alright? And the second is non-uniform circular motion. Now think about this. If I say that the fan is rotating at a faster rate or it is rotating at a slower rate, that means it is rotating such that the angle covered per second is more. We are moving on a circular path with a constant speed. Still our velocity is ever changing, and therefore, hello students, welcome back to another exciting class of physics where we are going to talk about a very special topic, that is vertical circular motion. So in the last class also we have talked about circular motion, but that was a general discussion on circular motion. Today we are going to talk about vertical circular motion. So can you understand what I am talking about? I am talking about something like this, maybe a windmill, right? A fan rotating on the ceiling. So that is a horizontal circular motion, isn't it? We are talking about vertical circular motion. So maybe a windmill can be an example of that. Even a pendulum for that matter. So you might wonder that a pendulum is not circular motion in that sense that it's going to complete the circular motion, but it is only a part of circular motion. Even then we refer it as vertical circular motion or circular motion, even if it is not complete but a part of it. Alright. So again, reminding you that since it is in continuation with circular motion, it is very obvious that you should watch that class first where we have discussed the basics of circular motion. Only then you would be able to understand how vertical circular motion works. Alright, so there is a lot to learn. Without wasting any time, let's get started. Put down the heading vertical circular motion. Alright, so first thing, so you might wonder, how did this question come up straight away? So that is how we are going to start today's class. Let's start with a question first and understand how the physics in vertical circular motion is working through a question. So what do we have here? A pendulum of length L and mass m is provided with a speed v is equals to root gl at its lowest point. So can you understand, there is a pendulum of length L and we have provided it with a velocity root gl. Find the ratio of acceleration at mean position and extreme position. Also find the angular amplitude of the pendulum. Give it a try and then we will get started with this. Alright, so you pause the video and give it a try. I am straight away starting with the solution now. So you would say that, okay fine, this is a pendulum. We have provided a velocity root gl at the lowest point. Now what is going to happen? Let's say it reaches up to this point. Okay. What do you mean by it reaches up to this point? Since we have provided a velocity, it will rise, and after a point its velocity is going to become 0, isn't it? If we go by the energy point of view, then we can say that we have provided it with a kinetic energy that is converting to potential energy as it is rising. Alright, so let's say it rises up to an angle of theta. Alright, so now the first thing that we can estimate this height. How? By using conservation of energy. So this is something that I am using, and you should have learned this in your previous classes, that when there is no friction, no air resistance, then there is always a compensation of energy. We have provided kinetic energy, which is half mv square, that is converting to potential as this bob is rising, isn't it? Alright, so very quickly let's do that. Let's assume that this angle, that is the angular amplitude. So you understand what amplitude is, the last angle it will go up to. Alright, so let's do that. So first let's write kinetic energy initial plus potential energy initial is equals to kinetic energy final plus potential energy final. So is this a circular motion now? Of course, yes. So that is why we are taking this as a part of today's topic. Alright, so the initial kinetic energy is going to be, let's say, half mv square, isn't it? It's going to be half mv square. Initial potential energy is going to be 0. Why? Because we have taken this lowest level as our reference. So we are starting off here, the potential energy is 0. Finally, the kinetic energy becomes 0, isn't it? Because we are talking about the last point it goes. Then it will come back. So this is a point with instantaneous rest where it's going to take a U-turn, isn't it? The potential energy, let's write it as mgh. So what is h then? This height that this pendulum this has achieved till the extreme position, this is, let's say, h. So I hope you understand this is going to be L cos theta, isn't it? If this is L, using the cosine, that is the base over hypotenuse, this is going to be L cos theta. So this whole is L and this is L cos theta. So we can write that H is equals to L minus L cos theta. Okay, so think about all this. I think you should be able to do it. Okay, so half m, and in place of v square we are going to write gl, because that is the velocity that we have provided at the lowest point, is equals to mg L1 minus cos theta. Alright, so we do that, mgl and mgl cancels out, so we get half is equals to 1 minus cos theta, or cos theta is equals to 1 by 2. So this class is in continuation with circular motion, that is why we are able to understand all this, and we can therefore predict that theta is equals to 60 degree. So the maximum angle it will go up to is going to be 60 degree, isn't it? So why are we doing this is the next question. Because they have asked us the ratio of acceleration at mean position and extreme position. Now, do you remember in the last class we have talked about centripetal acceleration, isn't it? We have talked about centripetal acceleration, which is responsible for changing the direction, isn't it? So let's talk about that here. Let's draw the free body diagram. So a lot to apply that we've learned in the previous classes. Let's draw the free body diagram also. We can do that also. So the tension is acting here and the weight is acting downwards, isn't it? And the net force towards center provides the centripetal force, isn't it? Never mind. So at initial position, what can we write? Acceleration is the centripetal acceleration, so that's going to be v square over r, isn't it? Now v square is like gl and r is also l, so this value turns out to be g. So what is the acceleration at this point? The answer is g, and this acceleration is basically the centripetal acceleration. Now think about this. When you have gravity, do you consider this as uniform circular motion? Is it uniform circular motion? The answer is no. It is not uniform circular motion because its speed is continuously changing. So let's revise that there are two types of circular motion, uniform and non-uniform. Uniform circular motion when speed remains constant, non-uniform circular motion when speed changes. So the speed here is continuously changing. So this is an example of non-uniform circular motion. Let's draw the free body diagram here now. So this is T2, this is mg, and this angle is obviously 60 degree that we have just found out. Now, since the velocity is 0 at the last point, can we say that the centripetal acceleration, at B, let's call this point as B, is going to be 0, isn't it? Why? Because v square by r is 0. Still, can it have an acceleration? Yes. Why? Because if we draw the free body diagram and we resolve mg, so this is going to be mg cos 60 and this is going to be mg sin 60. Agreed that these two will provide the necessary centripetal force, which in this case is 0 because v is 0. But what about this? So this is the acceleration which is bringing it back towards the mean position, isn't it? So can we say, so I hope you understand, when I say mean position, this position. When I say this position, that is the extreme position. Alright, so this force is unbalanced. So we can say that these two forces are balancing each other. but this force is unbalanced. So can we write that at B, mg sine 60 is going to be ma, and this a we can write as the tangential acceleration, because it is providing the acceleration along the velocity which is changing the speed. So in uniform circular motion, in case of uniform circular motion, only direction changes, but in non-uniform circular motion, magnitude and direction both change. So the tangential acceleration turns out to be g root 3 by 2, as sine 60 is root 3 by 2, and that is the acceleration at the extreme position. So what is the ratio of acceleration at mean position and extreme position? Is that what they are asking? Yes. So the ratio is going to be g is to g root 3 over 2, that is 2 over root 3. So are you understanding how the physics of this is working? And most importantly, now we have two versions of acceleration. So far in the last class, our focus was mainly on the centripetal acceleration, which was changing the direction. But as soon as we start with vertical circular motion, there is also a component of acceleration along the tangent that changes the speed, which is called the tangential acceleration. What was the next part? Angular amplitude. We have already determined that. So that turns out to be 60 degree. So it goes up to 60 degrees. So that's the angular amplitude. Such a wonderful question. So much to learn. Apply the concepts that you have learned so far, whether it be free body diagram, whether it be the concepts of circular motion, centripetal acceleration, all can be applied in the same question. Again reminding, even if it is not complete circular motion, still it is taken as circular motion, even if it is a part of circular motion. Okay, so this is part of circular motion. That's how pendulum will keep on oscillating, but since air resistance would be there, ultimately it will come to a halt. All right, so copy down the important stuff, then we move forward. All right, so after you know this question, you have understood a bit of it, I wish to talk about one more special case. What is that? To find the minimum speed needed at lowest point to complete vertical circular motion. So as we were discussing, most of you might have been anticipating that it would have been a complete circular motion, but it turned out to be a pendulum only in the previous case. So that is what I am asking now, that what velocity we should impart to this bob at the lowest point, minimum velocity, so that it is able to complete the whole circle, isn't it? So can you imagine, you have to provide it with a large velocity so that it completes the circular motion. Think about it. So let's call C as the center. This is, let's say, A. When it reaches here, let it be B, and ultimately when it reaches here, let it be D. Okay, so A, we have started the motion and we are wanting the circle to be completed. Now what is the problem? Why is the circle not being completed? The reason is this string. This string can slack, right? So as if we start with a low velocity, then it might just slack and not continue with the circular motion. Imagine you tie a bob with a string and you try to rotate it. If you don't do it with a high speed, you have very much a possibility that the string might just slack. So to keep it taut, you need to revolve it with a higher pace. So that is why our focus right now is at point D. Think about why should we focus at point D? The reason is, as it is rising, the speed is continuously decreasing. So the most difficult point to cross is D. So if we take a guarantee that point D is crossed, then we will ensure that the whole circle is completed, right? So a lot to learn again. Maybe a roller coaster functions like that you have to start with a minimum velocity so that it is able to complete the whole round. Okay, so let's do that. Now if let's say this is point D and the velocity when it reaches point D is Vd, so we draw the free body diagram. The tension is going to act in the downward direction, weight is going to act in the downward direction as well. What are we going to write? So let's write the equation at point D. As you know, net force is equals to ma, that is the Newton's second law. Let's do that. Td plus mg is equals to mvd square by L, isn't it? What have I written? Net force is equals to mass times acceleration. What is the acceleration? It is nothing but v square by r, since it is circular motion, right? So the value of Td turns out to be mv square by L minus mg. What do we want? We want that the string should not slack. The string should not slack. So we want the tension to be there. So for that we are making Td greater than equal to 0, isn't it? So this is going to be mv square by r minus mg greater than equal to 0. So Vd turns out to be greater than equal to root GL. So I hope you understand that if you want the circle to be completed, the velocity at point D should be greater than or equal to root GL. We can assume that equal to root GL will also do, because in that case tension will just become 0, but as soon as it starts moving forward, the string will again become taut. So this is what we want. Highest point, the velocity should be this much at least. But we are wanting to find the condition, what is the velocity we have to impart for it to complete the circular motion. What do we do then? We apply conservation of energy at A and D. Isn't it what you are thinking? That we have started off with some kinetic energy. As this is rising, kinetic energy is being lost and potential energy is being gained. So if this is the reference, then can we write potential energy at A plus kinetic energy at A is equals to potential energy at D plus kinetic energy at D. So what is the potential energy at A? So you would say it is 0. We have taken that as reference. What is the kinetic energy at A? So it is going to be half mva square. What is the potential energy at D? So that's going to be mg times 2L. Why 2L? Because it is the distance between A and D, which is nothing but the diameter. And what is the kinetic energy at D? So half mvd square. If we do that, we are getting Va square equals to Vd square plus 4GL, isn't it? Since Vd is root GL minimum, so for that Va minimum will be GL plus 4GL. So we want Va minimum to be root 5GL, isn't it? So can we write, if we want to complete the circular motion, the velocity at A should be greater than or equal to root 5GL. Why am I discussing all this? Because this knowledge is definitely going to be important for you to tackle situations like this, where some particle is completing a circular motion in the vertical plane. If you already have an understanding of this, it's always going to be an edge over the other students. That's why we are discussing all this here, and a lot to learn, a lot to apply. We have applied the concept of free body diagram. Let's draw the free body diagram at the lowest point also. Mg is going to act in the downward direction, but the tension always acts towards the string. It's a pulling force. It's going to act in the upward direction, isn't it? So that's about this particular case. You can copy down the important stuff and then we move forward. But more than just copying, you have to understand how we are applying everything that we have learned so far. All right, I will wait, pause the video, copy it down, then we move forward. All right, now let's do this again, but now with a twist. What is the twist? Now instead of a string, we have a rod. Just to discuss this, how things change. So now if it is a rod, we have to again find the minimum velocity needed if you want it to complete the circular motion, isn't it? So now if you think about this, the only difference now is going to be that the rod cannot slack. So the difference between a string and a rod is like this pen. It, even if the velocity is low, it cannot slack, right? Even if we place a weight here, it won't slack because it is rigid. So can we say that when it is at the highest point and we want it to complete circular motion, we would just want that even if the velocity here becomes 0, still it will be able to complete the circular motion. So you want to start it, you want to give it a velocity such that it just reaches here. Even if its velocity becomes 0, it will automatically complete the circular motion thanks to the fact that the rod is not going to slack. So what can we say? So we can say that Vd is 0. So all we want is give it a speed such that it reaches the highest point. So not to worry that whether the string is going to slack, because there is no string, now there is a rod, right? So we can straight away write energy at A is equals to energy at D, and therefore half mVA square plus potential energy is 0, because we have taken the reference where the potential energy is 0. We have assumed this as the reference. So this is going to be half mVd square plus mg times 2L. So 2L is basically the, again, the height of point D with respect to A, and what it turns out to be is that VA square is equals to Vd square plus 4GL. But if we want to find the minimum velocity, then we can take Vd as 0. So it's going to be 4GL. So VA minimum is going to be under root of 4GL. Or we can say that VA should be greater than equal to, there's no problem with providing a velocity more than root 4GL. But if you provide anything less than root 4GL, then it won't be able to reach the highest point and it will turn back, isn't it? So I hope you are gaining more confidence with every question that we do, and needless to remind you that we are going to start with the PYQs soon, and when we will discuss that, then you should gain more confidence on how things are to be done and applied in a particular situation, right? Copy down if you want to, and then we move forward. Alright, now let's talk about another aspect of circular motion, that is banking of roads or tracks. Again, a very important topic in general also to understand the application of circular motion in our daily life. So think about that, where I had discussed in the last class that we have to take a turn, then friction helps us to take a turn, isn't it? So imagine you are riding on a bicycle or in a car and you have to take a turn, then it is only because of friction that you are able to take that turn. Why? Because friction provides you that necessary centripetal force that is needed to take the turn. So again, so the style today that we are following is that we do a question first to understand the application. That's what we are doing here as well. In the situation shown, there is a gramophone record, and this gramophone record is rotating at 30 RPM. Alright, so what is omega? So that is 30 RPM. So to convert that to radian per second, we multiply by 2 pi and divide by 60. Why? Because rotations per minute, to make that per second, let's divide it by 60, and since one rotation is 2 pi radian, so multiply it by 2 pi. So this becomes in fact pi radian per second. This is the angular speed of this gramophone record. Now if the coefficient of friction between the coin and the record is 0.5, then find the maximum radius in which the coin can revolve without slipping, obviously. So we will draw the free body diagram. I hope you should be able to do that. mg, normal contact force, which you can write as Fn, and now if you think of this, it has to move on this circular path. So for that, it would need a centripetal force. Who's going to provide this centripetal force? The answer is going to be the force of friction. So can we say that force of friction is going to provide this necessary centripetal force, which we have learnt can be written as m omega square r, isn't it? So this force of friction, the maximum value, if we talk about that, then that's the limiting value of friction, which is mu n, that should be equal to m omega square r. Now Fn is equals to mg. So I hope you understand that the weight is making the normal contact and friction is providing the necessary centripetal force. So m cancels out, and that is why probably they've not given us the mass of the coin. So this does not depend on the mass of the coin. Even if it's a heavy coin, you might just believe that since it's heavy, it will have more friction, but it does not depend on mass. Why? Because if the friction is more, then the centripetal force needed is also more for a heavier mass. So what this turns out to be, so we would say mu is like 0.5 as given in the question. Let's take g as 10, omega is like pi square, okay, or let's take g as 9.8 only if nothing is mentioned. If they specifically mention, then we take it as 10. So let's take it as 9.8 only. So the value of r, we can just do the calculation very quickly. So this is going to be 0.5 times 9.8 divided by pi, and then again divided by pi. So what I am getting is 0.496. So let's take it as 0.5. All right. It's going to be 0.5 meters. So in centimeter, it has to be 50 centimeter, isn't it? Has to be 50 centimeter. Easy. What are we doing here? We are basically rotating a coin, and we are making use of the concepts of circular motion to understand how much force this coin is needing to move in this particular circular path, right? So without wasting any time, I think you should copy this down, and then we take another situation which is related with banking of roads. All right, I will wait here, copy this down, then we move. All right, so now you've understood how this coin is rotating or revolving, and now let's talk about what is going to happen when you are wanting to take a turn while driving in a car. So are you understanding what is the need of taking the turn? Because the road is bending like that, the path is bending like that, then obviously you have to be a part of the circle while you're traveling. Now imagine if we draw the free body diagram, the force that's going to act downward is going to be mg, the force that is going to act is going to be the normal contact, and friction is going to help you take the turn, isn't it? So even again, even if it is not a complete circular motion, it has to be a part of circular motion. So we can write that Fn is equals to mg, that is basically the equilibrium in the y direction, but in the x direction we can write that the net force in the x direction is providing the necessary centripetal force. And let's say if this curved path is of radius, let's say r, so let's imagine this is a part of a circle whose radius is r, then we can write this. And now as we know, if we are wanting to calculate the maximum speed, so that's the maximum possible speed with which we can take the turn. Are you understanding that? So can you imagine that if you are turning, you cannot increase your speed to after a certain limit. Why? Because if you are going to increase your speed and try to take the turn, negotiate that turn, then your car might just skid, isn't it? Why? Because friction, that is the provider of centripetal force here, has a limit. I hope you know that. Friction has a limit. Friction cannot go beyond a certain value. So if you are wanting to take the turn at higher speed, you need more friction. But then what is the limit? So that's let's say maximum value of friction, that is equals to m velocity maximum square over r, isn't it? So the maximum value of friction, as you know, is going to be mu n, that is mu times the normal contact force, and that's going to be mv max square over r. Now as we know, friction, the normal contact is going to be mg, and this is v max square over r. So the maximum possible speed is going to be under root of mu rg. You cannot take the turn at a speed more than this. Not that you have to mug up this expression, but you have to understand the situation, that how friction is providing the necessary centripetal force. All right. So can we do something if we have to increase the speed while taking the turn? Let's find out how we can have an alternate way, because friction has a limit. How can we achieve more speed and still take the turn? Let's find that out. First copy this down, then we move forward. All right, so this is the thing. Here we have bent the road, right? So why is it done? So already the civil engineers, the people who are constructing the road already know that it is a curved path. So just to help or support the vehicle, they bend the road, they bank it. Why? Because if they do that, the normal contact force that you achieve is going to be like tilted, and when that is the case, you have a component of this also helping you in taking the turn. So are you understanding? Just to take the turn at a higher speed, what have we done? We have basically tilt the road, and by doing that we are getting a component of the normal contact force, which is huge, to take the turn. So we are not only relying on friction here. Friction is of course there, but apart from friction there is a component of this normal contact which is going to help you take the turn. So this whole thing is called banking of roads. So imagine when there are cycle races, so they do, the tracks are purposely bent at a very high angle so that the cyclists can take the turn, or they can have the race at higher speed and still not skid, isn't it? That's what they do. All right, let's talk about one more case here. So just to eventually find that maximum possible speed, let's draw the detailed free body diagram. Okay, so the first force that we talk about is mg, then there is the force of normal contact, as you would know, and then of course there is some amount of friction as well. All right, so I hope you have drawn the free body diagram yourself and anticipated these are the three forces that are going to act on your car, right? So let's say you are moving on a circular path with radius, let's say r, okay, and let's do one thing, let's resolve the forces. All right, so as you would understand, this angle is going to be theta, as this is also theta, so this is going to be 90 minus theta, so this again is going to be theta. I just want to take the components. So the component of this is going to be Fn cos theta, and the component of this is going to be Fn sin theta. Are you understanding that apart from frictional force, now your normal contact force, you are also pushing the road obliquely and getting a force in the horizontal direction. Now let's resolve friction. So let's change the color here. Let's say the force of friction, that is going to be Ff cos theta, the component of friction that's going to act horizontal, and the other component is going to be Ff sin theta, that the frictional force sin theta. So what can we write now? We can of course write that in the y direction, Fn, right, in the y direction, we are writing this in the y direction. All right, so in the y direction, Fn cos theta, right, is equals to Ff sin theta plus mg. That's in the y direction. Now what about the x direction? So the x direction this time is going to be Ff cos theta, that is component of friction is of course there, but then there is another component of force, that is Fn sin theta, that will provide you the necessary centripetal force, and hence you should be able to take the turn at even higher speed. So that is what this banking of track facilitates. It provides you with more cushion, that you can acquire more speed and still take the turn. Now you can use these two equations to calculate the maximum permissible speed, but when maximum speed is achieved, we can say that friction will become equal to mu times Fn, isn't it? That's the maximum value of friction. Again, I am assuming that you know the basics of friction that we have discussed in our previous classes. All right, it is kind of something that you have seen around you. How the free body diagram is there, I think you should be able to understand, but this is something that is done to facilitate turning at higher speed. But what about two-wheelers like a cycle or a motorcycle? There is one more facility there, that they themselves can also bend. That is what we should talk about next. So this is what I am talking about, the bending of cyclist. So when I say bending of cyclist is basically, you know, when you are already knowing that you are wanting to take a turn, you bend your cycle like this. If I may draw it like this, then what's going to happen? Basically you are going to get the normal contact force at an angle, again facilitating the same thing. The friction is of course there, but now this normal contact force is also tilted, and that is why you can have the two components, mg acting downwards and then let's say Fn cos theta, and this is going to be Fn sin theta. So this is going to help you in providing the necessary centripetal force, which you may write very quickly that Fn cos theta is equals to mg, while Fn sin theta is going to provide the necessary centripetal force, that is going to be mv square by r. This is the equation in y direction, while this is the equation in the x direction. Solving the two, you get tan theta is equals to v square over rg, right? So v is equals to under root of rg tan theta. Whatever it is, one thing is certain, that if v is more, then theta is also more. So if you want to take this turn at a high speed, you need to bend more, isn't it? If friction is also there, then that is also going to assist you. But that is how the physics work here, that you tilt yourself, and by tilting you push the ground obliquely, and pushing it obliquely will give you a reaction also at an angle, and the horizontal component of the contact force provides the necessary centripetal force that is needed whenever you take a turn. Alright, let's do a couple of questions and end today's session, where we have, you know, learn more about circular motion. We'll keep doing that, but let's do a couple of questions. First you copy this down, then we move forward. Alright, so let's discuss this question. So in this situation, so it's kind of a death well where the car is moving on a vertical wall, right? And what is being asked? They are asking that what is the minimum speed that this car should have so that it doesn't fall. So now it is just the opposite. You need to ride fast, you need to drive fast if you don't want the car to fall. Let's understand why. So this is going to be the normal contact force, right, that the car is going to experience, and this normal contact force is going to provide the necessary centripetal force, isn't it? While if you draw the free body diagram of the car like this, let's say this is the car, so this is the normal contact force, weight is going to act downwards and friction is going to act upwards. All right, so now do you understand why do you need to drive fast? Because if you drive fast, the normal contact force will also increase, and if the normal contact force increases, then what happens is that you get more cushion, you get more friction, and this friction is, you know, stopping you from slipping on the wall. That is why you need to drive fast, so that you get more contact force. You get more contact force means you get more friction. So what should we write here? We will write that if it doesn't have to slip, then we should write that the friction should always be greater than the weight of the car. Now what should we write for friction? We should write for friction the maximum value, that is mu Fn. I hope you know that is greater than equal to mg. Now what is Fn? So that is mv square by r, that is greater than equal to mg, which implies that v should be greater than equal to under root of rg by mu. So you need this much speed if you want this to complete circular motion without slipping, right? So we can do this calculation now very quickly. So the value of r is given to be 5 meter, g is, as you know, 9.8, and mu is like 0.5. So this gives us v greater than equal to root 98, isn't it? So we can calculate the value of root 98 very quickly here. So the value is turning out to be 9.9. So the minimum velocity that you need to have here is 9.9, If you go to at a velocity less than that, then there is a risk that your car will slip. It's just the opposite. Normally the road is horizontal. Here you are driving on the walls, so the road becomes vertical in that sense. Right, let's do one more and end today's class. All right, so the next one, a cyclist riding at a speed of 11 meters per second attempts to make a sharp turn on a horizontal road. The turn can be modeled as a circle of radius, all right, 15 meters. So whatever turn it is taking, the radius has to be taken as 15 meters. State the forces that provide the necessary centripetal acceleration of the bicycle, all right. The coefficient of static friction between the bicycle and the bicycle tire and the road is 0.75. Deduce whether the cyclist will be able to take the turn without skidding. Outline how banking of the track can increase the maximum. So we have just talked about that. All right, so let's draw the free body diagram. Again, first let's assume that the cyclist is vertical. So mg, Fn, and the force that is going to help you take the turn is going to be the force of friction. All right, so what is the centripetal force needed? I hope you have attempted this by pausing the video and then only watching the solution. So the mass of the cycle is not given. V square is like 11 square and R is like 15. So when we solve this, it's going to be 121 divided by 15. So that is 8.1. 8.1 times m. That is the necessary centripetal force needed to take the turn at this pace. Let's see what is the maximum value of friction that is available. Maximum friction. So as you know, it is mu Fn, that is mu times normal contact force. So it's going to be mu times mg. All right. So mu is given to be how much? Mu is given to be 0.75 times m times g, that is 9.8. So it's going to be 0.75 times 9.8. So that is going to be 7.35 m, isn't it? What do you see? What do you see? That the friction that is available is 7.35 times the mass of the cyclist, while the centripetal force needed is 8.1 times the mass of cyclist. So the friction value that you can achieve is less than the centripetal force needed. Hence, turn cannot be taken. Hence, this turn cannot be taken. We cannot expect the cyclist to turn at this speed. So it has to reduce its speed, or the coefficient of friction has to be increased. The tire needs to be changed if you know this turning has to be done. So the answer to B part, whether the cyclist will be able to take the turn without skidding, the answer is going to be no. Outline how the banking can increase. So if we would have banked the road here, then obviously this turn would have been possible. Why? Because banking will also have a normal contact force helping you take the turn. All right, so we've done a lot in today's class. It was mathematically, a little more than usual that we have. But again, if you know the previous concepts really well, then this should not be a problem to you. But that's all for this particular class. Keep learning, and I'll see you next time. Happy learning. Bye-bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.